Mastering dynamic programming through core principles and pattern recognition. Dynamic programming stands as one of the most powerful algorithmic techniques in computer science, offering efficient solutions to complex optimization problems by leveraging overlapping subproblems and optimal substructure properties. This method allows programmers to break down seemingly insurmountable computational challenges into manageable components that can be systematically solved and reused. The key to effectively using dynamic programming lies not merely in memorizing algorithms but in deeply understanding the underlying principles that govern its application. By identifying patterns across different problem domains, developers can unlock new ways of approaching difficult computations while avoiding common pitfalls associated with naive recursive implementations. Fundamental concepts behind dynamic programming. Dynamic programming emerges from two essential characteristics found in many optimization problems: overlapping subproblems and optimal substructure. Overlapping subproblems occur when a recursive solution repeatedly calculates the same smaller instances of the problem, leading to inefficiencies. Optimal substructure means an optimal solution to the overall problem contains within it optimal solutions to subproblems. Recognizing these features enables programmers to transform inefficient exponential time solutions into polynomial time approaches. The transformation involves storing intermediate results through either memoization or iterative tabulation, preventing redundant calculations that plague straightforward recursive implementations. There are two primary implementation strategies in dynamic programming: top-down approach with memoization and bottom-up approach with tabulation. Top-down methods start with the full problem, breaking it down recursively while caching computed values. Bottom-up techniques begin solving smaller subproblems first before building up to larger ones iteratively. Memoization uses recursion combined with storage mechanisms, usually hash maps, to save previously calculated states, whereas tabulation employs iteration with arrays or matrices to build solutions incrementally. Both methods achieve time complexity improvements by eliminating redundant computation paths. While both approaches yield correct results, their performance considerations differ based on memory constraints and access patterns. Memoization offers flexibility at the cost of higher memory usage, while tabulation provides more predictable space requirements at the expense of additional initialization overhead. Overlapping subproblems occur when identical subproblem instances appear multiple times during computation. Optimal substructure guarantees that optimal decisions made at each step contribute to global optimality. Time complexity improvement typically reduces algorithm running time from exponential to polynomial levels. Spatial trade-off. Increased memory consumption is often necessary to achieve faster execution speeds. Classic problem types solved with DP. Certain types of problems consistently appear in coding interviews and competitive programming contests, exhibiting clear signs indicating dynamic programming applicability. These include sequence alignment issues where we must find optimal arrangements between elements with specific cost functions defined over them. Another recurring theme involves knapsack-style resource allocation dilemmas where limited capacity forces choices among items possessing different value-to-weight ratios. Problems requiring partitioning resources while maximizing returns typically benefit from dynamic programming frameworks. Longest common substring/supersequence computations exemplify another category needing dynamic programming treatment due to their need to compare sequences element-wise while preserving order relationships. When aligning strings with penalties for insertions, deletions, and substitutions, dynamic programming matrices provide structure. Fibonacci numbers calculation serves as an educational case study, demonstrating how even simple mathematical recurrence relations can become computationally expensive without memoization. While trivial on small inputs, naive Fibonacci implementations demonstrate why dynamic programming becomes crucial for scalability. Graph traversal and pathfinding represent yet another domain where dynamic programming shines. Finding shortest paths in graphs with arbitrary weights can leverage principles similar to those used in matrix chain multiplication and other classical DP applications. Common patterns in dynamic programming solutions. Despite appearing diverse at first glance, successful dynamic programming implementations often follow recognizable structural patterns. One prominent pattern is the use of multidimensional tables that capture state transitions required to compute final results efficiently. These tables organize potential state configurations in such a way that each entry represents some form of accumulated knowledge useful in determining future computations. Proper indexing and update rules ensure that dependencies between states get respected in computation ordering. A particularly useful structure is the 2D matrix employed in edit distance calculations between strings. Here, each cell corresponds to transforming one prefix of string A into a prefix of string B with minimum edits required. In the case of the longest increasing subsequence problem, a more clever approach than brute force enumeration leverages monotonic stacks along with careful tracking of current subsequence lengths under construction. This demonstrates that pattern recognition goes beyond mere table creation. It includes finding intelligent data structures and algorithm variants tailored specifically for particular problem families. Designing efficient state representations create meaningful abstractions that encapsulate critical parameters influencing the solution's decision-making process. Identifying which factors remain constant versus changing across computation stages helps determine appropriate dimensionalities for your DP array. Pick dimensions carefully to capture all possible relevant variations present in input data. Oversimplification might lead to incorrect solutions, while unnecessary complexity increases runtime and memory demands unnecessarily. For instance, handling coin change problems requires considering both available denominations and target amount. However, implementing this naively could result in O(n)² space complexity, which may be optimized further via smart dimension selection techniques. Consider whether certain dimensions can be represented implicitly rather than explicitly stored. For example, some problems permit recomputing intermediate variables instead of maintaining separate storage locations for them. Understanding temporal relationships between states matters significantly for designing effective update schemes. Sequential dependency chains require strict ordering when computing entries in our DP tables. Troubleshooting common implementation issues. Bugs frequently arise when developers misunderstand the actual nature of the problem being solved, especially regarding what constitutes valid or optimal transitions between states. Incorrect transition equations are a prevalent source of errors, stemming from misjudging what previous states can influence the current one or miscalculating how costs propagate through different operations. Some edge cases, notably empty inputs, single-element collections, or extremal numeric values, will reveal weaknesses in the initial formulations if they haven't been thoroughly tested up front. To debug effectively, try tracing through small sample inputs manually alongside the program's expected behavior, looking closely at every step until discrepancies emerge clearly. If an implementation works correctly on textbook examples but fails for more realistic scenarios, revisit fundamental assumptions about problem constraints and how they translate mathematically into code logic. Use print statements strategically to observe intermediate state values without overwhelming the output too much. Pay special attention to how boundary conditions get handled, since these often trigger cascading effects later on in the algorithm flow. Performance optimization techniques for DP algorithms. Even with optimal design, standard DP implementations sometimes fall short of meeting strict time efficiency requirements, prompting the exploration of various optimization techniques. Space optimization forms one crucial area where savings can be substantial. Often we only need to maintain recent layers of the computation rather than entire tables for all earlier steps, reducing memory footprint dramatically. Rolling arrays exploit this observation by keeping track of just enough information from prior iterations to allow progressing towards subsequent steps without discarding necessary data prematurely. The time complexity analysis reveals that many classic DP solutions operate within O(n)2 bounds, which can be prohibitive for extremely large n unless alternative approaches exist. Matrix exponentiation represents one advanced technique applicable primarily to linear recurrences, allowing us to jump ahead multiple steps simultaneously instead of calculating them individually each time. When applicable, approximations that guarantee near-optimal answers within tighter computational boundaries offer practical benefits where exactness isn't strictly enforced. Applications beyond traditional algorithmic's modern engineering problems increasingly rely upon principles originally conceived in theoretical contexts, showcasing versatility of dynamic programming across disciplines. Operations research utilizes DP extensively in inventory management, production scheduling, and route optimization tasks where discrete choice points heavily impact long-term outcomes. Artificial intelligence systems employ modified versions of standard DP approaches for reinforcement learning scenarios involving Markov decision processes with uncertain rewards modeled probabilistically. Bioinformatics depends critically upon dynamic programming for genome sequencing alignment, where matching DNA strands against reference databases requires scoring various local and global alignments accurately. Economics models make use of backward induction procedures inspired by game theory analyses, which essentially mirror recursive decomposition techniques central to DP methodology. Network routing protocols apply dynamic programming principles to route discovery processes where pathfinding involves evaluating trade-offs between bandwidth utilization versus transmission latency objectives. Education and practice strategies for mastering dynamic programming. Gaining fluency with dynamic programming concepts requires deliberate practice targeting foundational skills while gradually moving toward increasingly sophisticated problem sets. Beginners should prioritize recognizing characteristic markers pointing toward applicability of DP solutions before attempting formal derivations, developing intuition for real-world scenario recognition. Working through classic textbooks containing well-curated collections of exercises provides structured progression from basic concepts to nuanced refinements that advanced learners encounter. Coding platforms specializing in algorithm challenges serve as invaluable laboratories where one can implement and test hypotheses around varying problem structures. Maintain documentation logs capturing insights gained from failed attempts. Analyzing dead ends often yields lessons more instructive than straightforward successes ever could. Seek mentorship opportunities whenever encountering persistent conceptual difficulties, focusing on resolving misunderstandings early rather than perpetuating misconceptions through repeated trial-and-error cycles. Cultivate curiosity about related fields where dynamic programming principles manifest indirectly, deepening comprehension through interdisciplinary perspectives that contextualize core ideas. Coding bootcamps and online courses providing curated tracks for dynamic programming mastery help organize study plans while connecting individual topics cohesively within broader technical ecosystems. Build muscle memory through targeted drilling sessions reinforcing essential mechanics involved in writing clean, maintainable DP implementations that scale gracefully with growing input sizes. Future directions in dynamic programming research. Ongoing academic investigations continue exploring novel methodologies aimed at extending traditional DP paradigms into uncharted territories while refining existing techniques for better adaptability across modern computational landscapes. New developments focus heavily on hybrid approaches combining strengths from different algorithm classes including greedy, divide and conquer, randomized, and machine learning enhanced solutions. Research efforts seek to create self-improving systems capable of automatically discovering suitable DP formulations given high-level descriptions of desired outcome specifications. The integration of parallel processing architectures promises significant speedups for certain categories of DP problems amenable to decentralized execution patterns. Variants designed for quantum computing environments represent frontier work addressing challenges unique to qubit-based hardware constraints while exploiting inherent parallelism offered by superposition states. In academia, continued emphasis remains on theoretical foundations, ensuring rigorous proofs accompanying any proposed extensions to established DP methodologies. Cross-disciplinary collaborations between mathematicians, engineers, and software architects foster innovation that transcends conventional disciplinary silos, limiting creative problem-solving approaches. Conclusion: mastering dynamic programming entails cultivating a deeper appreciation for both the architectural elegance and practical utility embodied in its methodologies. Success derives from recognizing patterns that transcend specific problem formulations. The journey towards proficiency begins with acknowledging personal limitations while embracing growth through consistent exposure to varied challenge types that broaden conceptual horizons progressively.